So just some more harder questions now. So we have a diagram showing a proton moving through an electric field. Now we've got 0 volts, 100 volts, and 200 volts. So the proton goes from 0 volts up to 200 volts. Okay, so first of all, we need to determine which side of this electric field is more positive. Okay, so is it going to be the top or bottom that's more positive? Who's got the answer? Right, so remember that as the potential is higher on this side, it's going to be more positive. Okay, so the potential tells you which side is more positive. Okay, so this side is positive and this side is negative. All right. So if you're a proton, you're positively charged, and so you don't want to go towards the positive side, you want to go towards the negative side, right? So this proton at point A, it initially had a speed of 3 times 10 to the 5 meters per second. So we'll write that down. The initial speed, so the initial velocity of the proton was 3 times 10 to the 5 meters per second. And we want to know what the final velocity is going to be when it's reached this point here. Okay, so if this proton is getting repelled by the positive side, then it's going to be losing velocity, right? Because it's going to be there's going to be a force acting this way on it. So we can imagine that the change in kinetic energy is going to be negative. So we need to find out, first of all, the initial kinetic energy that this proton had. So the initial kinetic energy will be half times mass times the velocity squared. And so the mass of a proton, that's going to be on the front of your formula sheet, and that's 1.67 times 10 to the negative 27. Okay, and the velocity was 3 times 10 to the 5, and that's squared, and that will give you a 7.515 times 10 to the negative 17 joules. Okay, so that's your initial kinetic energy, right? So I'm just going to rub that out and write it up here, just because I'll need some space, because this is a pretty hard one. So the initial kinetic energy was 7.515 times 10 to the negative 17 joules. Okay, so we have that. And so then we need to calculate the change in kinetic energy. All right, so the change in kinetic energy is going to be equal to the change in its electrical potential energy, because it's moving through an electric field and it's electric forces that are acting on it. And if you have an electric particle moving through an electric field, that's the charge multiplied by the change in voltage or the change in potential. Okay, and so that's going to be Q, which is the charge of a proton. So it's a proton, so the charge of a proton is 1.6 times 10 to the negative 19. And then the change in potential is going to be, it's gone from 0 to 200, so that's 200 volts. And that will be 3.2 times 10 to the negative 17 joules. Okay, so we've got the change in our kinetic energy. And remember that it's going to be losing this kinetic energy, right? Because it's a positive charge going towards the positive side, so it's going to be repelled. So our final kinetic energy will be the initial kinetic energy minus the change in kinetic energy. Okay. So at point B, it's going to have 7.515 times 10 to the negative 17 minus our change, which is 3.2 times 10 to the negative 17. So that's 4.315 times 10 to the negative 17 joules. Okay, so that's our kinetic energy that we'll have when we're at point B. So now that we have the kinetic energy, we can now calculate what our velocity is going to be. So remember that kinetic energy is equal to half mv squared. So if you rearrange that, velocity is equal to the square root of 2 times the kinetic energy divided by the mass. So that's an equation that you should have on your cheat sheet. Okay, so the final velocity is equal to 2 times the kinetic energy, which is 4.315 times 10 to the negative 17, divided by the mass, which is 1.67 times 10 to the negative 27. And if you do that, that should give you 2.3 times 10 to the 5 meters per second. Okay. So you might be asking, why didn't we just use the change in velocity will be equal to the change in kinetic energy? So you've got the change in velocity is equal to 2 times the change in kinetic energy divided by the mass. So you can only do this when the initial velocity is 0. Okay, so because of the fact that kinetic energy is proportional to the velocity squared, it's not when the initial velocity isn't 0, it's a different change in velocity compared to when. All right, so to put it this way, if you start off at initial velocity of 0 and you add a certain amount of kinetic energy, and let's say you increase your velocity by 10 meters per second, and then you added the same amount of kinetic energy again, that's not going to result in an increase of 10 meters per second again. It's going to be less than that. Okay, so in the cases where you have an initial velocity already, you have to calculate the initial kinetic energy, calculate the change in kinetic energy, and then calculate the final kinetic energy, and then get the final velocity from that kinetic energy. So it's going to be a lot more steps, but that's the way you have to do it. So if you want an example of that, I think that's like number 5 or so in the last year's exam. So in last year's final exam, 2018, they had an example of finding the velocity when the initial velocity wasn't 0. So you can have a go at that. So number 2 what is the magnitude and the direction of the electric field at a point 2 meters to the right of a negative 0.5 microcoulomb point charge? Okay, so we have our negative charge here, and it's negative 0.5 microcoulombs. Okay, so if it's a negative charge, the electric field will always be directed in towards the negative charge. Okay, so if we're 2 meters to the right of it, if we're here, then the electric field here would be pointing that way from the negative charge. Okay, so we know that the electric field, the direction of the electric field has to be pointing to the left if we are standing to the right of it. Okay, so it's going to be either B, C, or E, and you can cross off A and D, right? Now, the equation that you're going to use is you want to calculate the the strength of the electric field now. So that equation is the electric field strength is equal to the force felt by a charge. Okay, so F over Q is the amount of force that's felt by a charge in an electric field. Okay, so we can place a charge here at this point, and we can calculate how much force it's going to feel from that charge, and that's how we can calculate it. So to make things easy, let's make this a positive charge. So this will be a positive charge, and the easiest way to do it is to make this a 1 coulomb charge. Okay, so you've got a positive 1 coulomb charge here, so that when you calculate the force, it'll be divided by 1. Okay, so that's really easy. So in order to calculate the force, the electrical force, that's force is equal to K times Q1 times Q2 over R squared, right? So that's going to be, K is a constant, that's 9 times 10 to the 9. And Q1 is, so you can use either one, it doesn't matter. Q1 is 0.5 times 10 to the negative 6. So that's the microcoulomb. And then the other one, Q2, is 1. And then the distance, so R is the distance between the two charges, so that's 2 meters. So 2 squared. And so then that will give you an answer of 1,125 newtons. Okay, so then we can plug that into our electric field strength formula. So that's 1,125 divided by 1, which was our charge. So that's just 1.13 times 10 to the power of 3. Okay, so that's going to be option C. All right. So this is quite a hard one. So don't worry if you didn't quite get it right at the start. Now we have 3 capacitors, and 2 of them are in series, and then the other one is in parallel. Okay, so I think everyone knows how to calculate resistors in parallel and series. And then so with capacitors, it's just going to be the opposite of that. So if you have capacitors in series, that's going to be the C total is just C1 plus C2. Oh no, sorry, my bad. Sorry, this is for parallel. So if you have them in parallel, it's just C1 plus C2. And then if they're in series, C total is equal to C1 to the negative 1 plus C2 to the negative 1, and all of that to the negative 1. Okay? So the bottom two okay, so these bottom two here, these are in series, so we're going to have to add them up first. So when we add them up, they're going to be 1 over CB plus 1 over CB, okay? And so that's just going to be 2 over CB. And then, so remember, all of that is to the negative 1. So if it's to the negative 1, that means that you're going to flip it. Okay, so that's the same thing as CB over 2. Okay, so that's this part here down there. So then, and then you have CA here. So since these two are in parallel, you can now just add them together. So C total is equal to CA plus this part down here, which is CB over 2. And CB divided by 2 is the same thing as half times CB. Okay, so that's going to be our answer. Option B. Okay, so that's just a real mathsy kind of one. A lot of algebra. All right. Number 4, we have an electronic flash gun, which uses a 15 microfarad capacitor to store energy, which it then discharges. You have the total resistance, which is 100 ohms, and then the potential is 100 volts when it's fully charged. So I want to find the maximum energy that can be delivered in joules. So that's going to be U is equal to half CV squared. So half times the capacitance, which is 15 microfarads. So 15 times 10 to the negative 6 times the voltage, which is 100. So 100 squared. And that would give you 0.075 joules. Okay. Number 5, how long does it take for the capacitor to discharge to 1 over E squared of its initial value? Okay, so 1 over E squared, that's the same thing. If you did that on your calculator, So you could do, on your calculator, you could do e to the negative 2 if you wanted to check. That's going to come out as 0.135, which just rounds to 0.14. So that's 14%. Okay, so it's asking you how long does it take for the capacitor to discharge to 14% of its initial value. And that's going to be 2 time constants. So we're going to find out what 1 time constant is, and that's RC. So resistance is 100, and the capacitance is 15 times 10 to the negative 6 microfarads. So that's 1.5 times 10 to the negative 3 seconds. That's 1 time constant. And then 2 time constants would be 3 times 10 to the negative 3 seconds. Okay? So pretty simple for those two. Number 6 is a little bit harder. So we have our circuit with quite a few resistors. So we want to find out how much current is going through the 100 ohm resistor labeled R4. Okay, so we can see that it's part of a parallel circuit. So if I quickly draw it, so here's our first resistor, our second resistor, and then I'm going to draw it a little bit differently, but this is exactly the same. Exactly the same circuit, just drawn slightly differently. Okay, so this is 100 ohms, 200 ohms, 100, 300, and this is 125 ohms. Okay, so if we're a charge, we're going to come out, go through here, go through these two resistors, and then when we get to this point here, we can choose to either go down this side and come through, or we could go to the other one and come through this way. So you've got a choice here whether to go through the left one or the right one. Okay, so you're only going to have a proportion of the total current going through one of these. Okay, so this one on the left has a lower resistance, so more of the current will choose to go through, well, not choose, but like more of the current will go through the left resistor, okay, because it's got a lower resistance. And so that means the current on the left will be greater than the current on the right, and so it's going to be proportional. So since the resistance is 3 times lower, the current will be 3 times greater, okay, because current is equal to V over R. So if resistance is tripled, so if resistance is decreased by a factor of 3, then the current will increase by a factor of 3. Okay. So yeah, so there'll be 3 times more going through this side compared to this side. Okay. So now we know the proportion is going to be 3 parts to this side and 1 part to this side. So that means 3/4 of the total will go through here. So 3/4 of the total will go through the left one, and 1/4 of the total will go through the right one. So we know the proportion. Now we need to know the total so that we can calculate how much is actually going through. Okay. So to do that, we need to figure out the total resistance of the circuit. And first of all, we're going to figure out how much this part, this parallel, these two what the effective resistance of these two are. Okay, so these two is going to be the resistance in parallel is going to be R1 to the negative 1 plus R2 to the negative 1 to the negative 1. Okay, so that's 100 to the negative 1 plus 300 to the negative 1, all of that to the negative 1, and that will give you 75 ohms. Okay, so then we can add it all up. So 100 plus 200 plus 75 plus 125, that's going to give you a total resistance of 500 ohms. So R total is equal to 500 ohms. And then the total current will be equal to the total voltage divided by the total resistance. Okay, so the total voltage was 10 volts and our total resistance is 500. So that will give you 0.02 amps. So that's the amount of current that's coming out of the battery. So 0.02 is coming out, and then it's getting to this point here. Some's going down this way, and some is going down this way. Okay, so 3/4 will go down here, and 1/4 will go down here. Okay, so the amount that we want to know is the amount going through here. So the current going through resistor 4 is going to be 3/4 times 0.02, and that's going to be 0.005 amps. So, sorry? 0.015? Which, this one? Yeah. This one? Yeah. Okay. Oh yeah, sorry. 0.00, oh yeah, sorry. 0.015. Is that it? Yeah. 15. Sweet. Thanks. So that's 15 milliamps. Okay. Cool. Thanks for that. Okay, so that's going to be option C, right? Number 7, we have a scuba diver sitting at the bottom of a 5-meter deep swimming pool, which is filled with water. He shines a green laser upward at an angle of 50 degrees to the vertical. So what angle will the light leave the water? So we have this is the surface of our water. And then the light's coming in. So that's coming in at an angle of 50 degrees. So that's angle 1. Okay. And the refractive index of the water is 1.33. So that's N1 is equal to 1.33. And if it continue straight on this line, it would go this way, but once it hits the air, it's going to increase in speed. And so that means that it's going to refract and it's going to bend. So we want to know what the new angle will be from the vertical when it leaves this water. Okay, so when it's leaving the water, if it speeds up, it's going to bend this way, away from the normal, so it's going to bend down this way. Okay, Now the equation for that is n1 times sine of angle 1 is equal to n2 or times n2 times the sine of angle 2. Okay, and then you can have it rearranged for the angle 2, which is inverse sine. So then n1 times sine of angle 1 over n2. Okay, so usually you'll be asked for angle 2. So we'll put those numbers in. So sine to the negative 1. So n1 is 1.33. And then sine of angle 1, which is 50, over the n2. So since it's going into air, n2 will be 1. So the refractive index of air is just 1. And if you do that in your calculator, you will get an error. Okay? So if you're getting an error, what does that mean? What's happening? Yep, thanks. So total internal reflection is occurring. So this light ray is bending so much that it's actually going this way. And if that happens, it's not going to be able to leave the water. Okay, so that's total internal reflection. So your answer there would be E. So then if you're really paranoid and you want to check whether that was right or not, so you want to calculate the critical angle. So let's say you calculate the critical angle. So you're going to see what's the minimum angle for that total internal reflection to occur. So that would just be the inverse sine of n2 over n1. Okay. So that would be n2 is 1 and n1 is 1.33. And I think it was something like 48 degrees or something. I can't remember. But so that means that anything above 48 degrees is going to result in total internal reflection. So you can see that that's correct, because when we came in at 50 degrees, we had total internal reflection. Okay? So number 8, we have a 1.65 meter tall person focused on by a human eye. The image, so that's the height of the object, 1.65 meters. And then the image, which is formed on the human retina, so that's the height of the image. That was 2 millimeters high. And inverted, so it's upside down, so the out of image will be negative. So negative 0.002 2 meters. And then we have the DI, so that's the lens to retina distance. So remember, the image is forming on the retina, and the distance is 2 centimeters, so 0.02 meters. And then what we want to find out is the distance of the object. Okay. So we've got this equation, HI over HO is equal to negative DI over DO. Okay, so what we want to find is DO. Okay, so it's on the bottom, so we can just flip it upside down, both sides. So we can flip it, HO over HI is equal to DO over negative DI. Okay, so we've got DO on the top now. And then we want to get DO on its own, so we can just send negative DI up to here. So that's HO times negative DI over HI equals DO. Okay. So DO is equal to 1.65 times negative of DI, which is 0.02, and then divided by negative 0.002. So that will give you 16.5 meters. Okay. Number 9. Number 9, we have a telescope, and it's got a magnification of 20. And assuming that your telescope is optically perfect, and so the eyes are limited only by diffraction, what is the smallest object that he could resolve on the surface of the moon? Okay. So the situation is, it's asking for the smallest object that you can resolve, but to make it simple, I'll just do it as if it's two objects that, what's the minimum distance between two objects that he can resolve, because it's pretty much the same thing. Okay, so we want to know what the minimum distance or the size of the object that he could resolve. And then, so this is on the moon. And then you're going to have, so this is going to be his pupil. And the pupils have a diameter, all right? And then it's going to hit the retina at the back of his eyes. Okay. So when the light goes through the pupil, it's going to diffract and it's going to spread out. Okay, so the image will become blurry. So obviously if these objects are close together, or if it's a smaller object, then the angle will be smaller. So then these arrows might overlap. Okay, so we're looking for the minimum distance where these arrows will not overlap. Okay. So if you draw it like this, then the distance between here is y, and the distance from the objects to your aperture is going to be x, so you've got x and y. And then the diameter of this circular aperture is d. And then the wavelength, the wavelength of the light is lambda. Right, so you've got your variables there. So what we're looking for is y. So here's our equation, y over x. So y over x is equal to 1.22 times the wavelength over d. And so we want y on its own, so we're just going to send x up onto here. So x is now on the top. So we'll get rid of this boy. So y, so 1.22 times the wavelength, so that's 500 nanometers. So 500 times 10 to the negative 9 times the distance to the moon, which is 384 times 10 to the power of 6 meters. And then it's going through his pupil, which is 5 millimeters wide. So that's 5 times 10 to the negative 3 meters. Okay. So that will give you 46,848 meters. Okay, so then you have to remember that the telescope had a magnification of 20, so you're going to be able to resolve 20 times higher. Okay, so you're going to divide that by 20, and that will give you your answer. So that's going to be 2,300 meters, which is 2.3 kilometers. Okay? So this is for circular apertures, all right? Number 10, you have your patient has a near point located 90 centimeters from his eyes. He's got contact lenses which allow him to read a book held 25 centimeters from his eyes. And the patient has a lens to retina distance of 2 centimeters. What is the power of the contact lenses? So this time we're looking for the power of the contact lenses. Okay, so the power of a lens is equal to DO to the negative 1 plus DI to the negative 1. And so the object here will be the book. So the distance of the object, the book, is 25 centimeters. So 0.25 to the negative 1. And remember this time, for this one, the contact lenses are right on his eye, so there's no difference in distance. And then so DI here, so the image distance is going to be the near point, which is 90 centimeters from his eyes. Okay? So remember that if you have corrective lenses, the lenses are going to create an image at the person's near point. Okay? And it's going to be a virtual image because it's got to be on the same side as the object. So remember what I said in the first tutorial? I said a virtual image for a lens will be on the same side as the object. Okay, so it's going to be a virtual image at the person's near point on the same side as the object. So that's going to mean that the DI, the image distance, will be negative because it's a virtual image. So it'll be negative 0.9 meters. Okay. And yeah, so you don't need to use the lens to retina distance in this scenario, and that's going to give you 2.89. Right? Number 11 is a very common question. So you have an alpha particle which is accelerated from rest through a potential of 3 kilovolts, and you want to find out the final speed. So remember that an alpha particle is 2 protons and 2 neutrons. So it will have a charge. So the charge of a proton, the charge of an alpha particle will be equal to the charge of 2 protons because there's no electrons to cancel out the positive charge. So that's going to be 3.2 times 10 to the negative 19. Okay, so that's very important to remember. The charge of an alpha particle is 3.2 times 10 to the negative 19. And then the change in kinetic energy of a charged particle that's moving through a potential difference is equal to Q times V. Okay, so Q is the charge, 3.2 times 10 to the negative 19. And the potential difference, the V, is going to be That's going to be 3 times 10 to the 3. Okay. And then you could put that into the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. So we could do that. Or you could do it all in one go, so you don't have to use 2 equations. So you could do 2 times, so the kinetic energy is QV, so we'll just put QV in here, divided by the mass. Okay, so you can have that on your cheat sheet as well. This one's running out of. So 2 times 3.2 times 10 to the negative 19 times 3 times 10 to the 3 divided by the mass, which is 6.6 times 10 to the negative 27. And that will be 5.4 times 10 to the power 5. Okay. Yeah, so that's also a good one to have on your cheat sheet. Number 12. So we have a decay, and we want to know what particle is released. So you're going to look at the top number. The top number doesn't change. So 231, it stays at 231. But the bottom number is increasing, so it becomes 91. So that's increase of 1. So that's going to be beta minus decay. So it's going to be beta minus decay. So you're producing a beta minus particle, which has a mass number of 0 and a charge number of -1. Okay, so that's going to be beta minus. Okay. So just remember, for beta decay, if the atomic number goes down, it's beta plus. If it goes up, it's beta minus. So it's kind of like the opposite. So number 13, a typical banana contains 50 micrograms of potassium. The half-life is 1.248 billion years, or 3.94 times 10 to the 16 seconds. So you want to find out how many nuclei are decaying each second. So the number of molecules that are decaying per second, that's the activity. So we're looking for the activity. So activity is equal to the decay constant multiplied by the number of molecules. So we'll find out the decay constant. Decay constant is 0.693 divided by the half-life. And the half-life is going to be in seconds. So 0.693 divided by 3.94 times 10 to the power 16. And that's going to be 1.76 times 10 to the negative 17. So that's your decay constant. And now you need to find out the number of molecules. So what we have there is the mass. So we're going to have to turn the mass into moles, and then the moles into number of molecules. So the number of moles in a mass is equal to mass divided by the molar mass. Right, so I'm sure you all remember that from chemistry. So the mass is 50 micrograms, so we have, because the molar mass will be in grams, we'll convert the mass into grams as well. So 50 micro is times 10 to the negative 6. divided by the molar mass. So the molar mass is the top number on your element, so that's 40. So we have 1.25 times 10 to the negative 6 moles. And then the number of molecules will be equal to the number of moles multiplied by Avogadro's number. So that's 1.25 times 10 to the negative 6 times 6.02 times 10 to the 23, which will give you 7.525 times 10 to the power of 17. So you finally got your number of molecules. Now we can plug that all in to our equation. Our decay constant is 1.76 times 10 to the negative 17. And our number of molecules is 7.525 times 10 to the power of 17. So our activity is going to be 13.2 becquerels. Okay, and remember that 1 becquerel is equal to 1 decay per second. Okay, so that's our activity. Whew. Number 14. So blah blah blah. You got what's the energy of the K alpha line your X-ray machine will produce, and you want that in kilo electron volts. So you want energy of K alpha. That's really simple. You're just going to use this equation. 10.2 EV Z minus 1 squared. Okay, 10.2, and we want the energy to be in electron volts, so we don't have to convert that into joules. So it's just 10.2 times Z. So Z is going to be your atomic number, which is the bottom number next to the element. So that's 30 minus 1 squared. And that will give you 8,578 electron volts, and that's 8.58 kilo electron volts. Okay. Number 15. You've got a 65 kg patient who absorbs a full body dose of 0.25 rem during the course of the treatment, in which a gamma emitter is used. So the gamma photons have an energy of 0.5 mega electron volts. You want to find out how many photons were absorbed by the patient. Okay, so in order to find out the number of photons, so the number of photons will be equal to the total energy divided by the energy of one photon, right? So the reason for that is because the total energy, remember, is made up of photons. So the energy of the photons of one photon times the number of photons would give you the total energy. So that's just rearranged. Okay, so the number of photons is the total energy divided by the energy of one photon. So we already know what the energy of one photon is. We need to find out what the total energy was. All right. So in order to do that, what we know is that they've got 0.25, they've received 0.25 rem. Okay, so remember that rem is a unit of effective dose. Okay, so for effective or equivalent dose, the units is sieverts, and 1 sievert is equal to 100 rem. And when you, in order to calculate the effective dose, you multiply your absorbed dose by the RBE. So RBE is the relative biological effect, which tells you how damaging that type of radiation is. Okay, so the RBE of gamma is just equal to 1. Okay, so that means that the absorbed dose will be equal to the effective dose. Okay, so if we have the effective dose, which is we've got 0.25 rem. So 0.25 rem will be equal to, so you'll divide that by 100, and that will be 2.5 times 10 to the negative 3 sieverts. Okay, so that's the effective dose, and the effective dose will also be equal to the absorbed dose. And then absorbed dose is equal to energy, the total energy divided by the mass. And so that means that the energy is equal to the absorbed dose times the mass. Okay, so that's the absorbed dose was 2.5 times 10 to the negative 3 times the mass, which is 65 kilograms. So that will give you 0.1625 joules. So that's the total amount of energy that was absorbed by this person. Okay, so I'm going to rub this stuff out. So E total equals 0.1625 joules. And then, so now we need to convert the energy of the photon. That's been given to us in mega electron volts. So we have to turn that into joules. So 0.5. So mega is million. So that's 0.5 times 10 to the power of 6 times 1.6 times 10 to the negative 19. So the energy in each photon is 8 times 10 to the negative 14 joules. So now we have the energy of photon and the total energy, so we can plug that into here. The number of photons is equal to the total energy, 0.1625, divided by the energy in one photon, which is 8 times 10 to the negative 14. And that will be 2.03 times 10 to the power of 12. Okay, so option D. All right, so we finished just on time. So that's it for this semester. Thank you very much for attending my tutorials. It's been a pleasure to teach all of you. I hope I've been able to help you guys. So I tutor Bioc 192 as well. So I've told Chris that I'm available. So I might be coming back next semester, but we're not sure yet. Okay, so good luck for all your exams. And if you have any questions, you can message me. All right, cool. Good luck, guys. Thanks. Cheers.